this lesson, we're going to be learning how to determine the general or the complementary solution of a recurrence relation. So, the method which we're going to use here is the method of undetermined coefficients. So, what does this mean? Well, the name is self-explanatory, right? Method of undetermined coefficients, meaning our solution is going to be in terms of coefficients which we don't know the actual values of unless given initial conditions, which will talk about what exactly are initial conditions. So let's have the first example which we classified already. We had y subscript k minus 3 y subscript k minus 1 minus 4 y subscript k minus 2 is equal to 0. Well, how can we solve this difference equation or a recurrence relation? So the method here is so easy. First of all, you have to assume a trial solution. So if you're taking mathematical modeling class, you don't have to know why you pick such a general solution. So our solution will be of this form: y sub k equal to some variable a multiplied by lambda to the power of k. Now we found this, right? Is this. Now I have to be able to find yk minus 1, and I find it by replacing k minus 1 in the space of k in this expression here. So this means that y sub k minus 1 is equal to a lambda. Where I see k, I'm going to put k minus 1. Okay. Now I can break this into a lambda k multiplied by lambda to the power of 1, which is just simply a lambda lambda k. Y subscript k minus 2, I do the same thing. Here and here, I put k minus 2. So y sub k minus 2 is going to be equal to a lambda k minus 2, which is equal to a lambda k multiplied by this was negative 1 actually, okay, and then lambda to the power of negative 2. So now we have identified these three things. So I'm gonna take them and put them in that expression where I found them. So with y sub k minus 3, y sub k minus 1 minus 4, y sub k minus 2 and equal to 0. So where I see this, I'm going to put this, okay? I'm going to have a lambda to the power of k minus 3. Then here I'm going to put this for yk minus 1. So it's a lambda to the power of negative 1, lambda to the power of k. Then minus 4 multiplied by what? A lambda to the power of k minus lambda to the power of multiplied by lambda to the power of negative 2. Then we equate that to 0. Well, let's try to simplify. I've got a lambda to the power of k minus 3. Well, this is the inverse, so we can take it to the bottom. Then I've got lambda k minus 4. Same applies to this. You take it to the bottom and it changes the sign, right? So we still have a there. And then lambda to the power of k divided by lambda squared, and you equate that to 0. Now we've got a common factor of a lambda k, a lambda k, and a lambda k. So this is what I'm going to take out as a common factor. So a lambda k, if I take it out as a common factor, here I'm left with 1, and here I'm left with negative 3 over lambda, and here I'm left with negative 4 over lambda squared equal to 0. Now I'm multiplying two numbers, which I say they must be equal to 0. If I say 2 times 3 equal to 0, okay, this is not valid. Let's say we say x times y equal to 0. This means that either x equal to 0 or y equal to 0. It doesn't have to be both. As long as one of them is true, then overall scenario is true. So now this means that a lambda k is equal to 0 or 1 minus 3 over lambda minus 4 over lambda squared equal to 0. But when we started, we said we are assuming a trial solution. We said this was a trial solution, and it must be non-trivial, meaning it must not be 0. So when you say a non-trivial solution, we mean it must not be equal to 0. This means that a lambda to the power of k must not be equal to 0. Therefore, this puts strain on this one. If x times y is equal to 0, but x is not 0, it's obvious that y is the one that must be 0, right? So this means that 1 minus 3 over lambda minus 4 over lambda squared must be equal to 0. I'm going to multiply all the terms by lambda squared. If I do that, I'm going to have lambda squared times 1, which is lambda squared, minus lambda squared divided by lambda, going to be minus 3 lambda, and then minus 4 equal to 0. Okay, so let's move down the page. Now let's see what we get. We must be able to solve this equation, right? So now let's see. If we try to solve this by factorization, I'm going to have lambda here, lambda. I look for two factors of 4, which is going to be 4 and 1 in this case, which can give us a negative 3, right? So you must be able to solve quadratic equations. So now we've got two solutions here. Lambda 1 is equal to negative 1, or lambda 2 is equal to 4. Remember what we said? We said our trial solution was given by what? Was given by y sub k is equal to a lambda to the power of k. Now, since I've got two values of lambda here, I must extend this to be lambda to the power of k. But I'm going to have two values of lambda, so I must say lambda 1, lambda 2. So this form here will give me something called my complementary solution or my general solution. So you can even replace this y sub k with y sub c, so that we are dealing about with the complementary solution. So for you to find the complementary solution, y sub c is equal to a lambda 1 to the power of k plus b lambda 2 to the power of k. Let's put the value of lambda 1 and the value of lambda 2. I'm going to have y sub c equal to a, which we don't know what it is, but we know lambda 1 is negative 1 to the power of k, plus b multiplied by lambda 2, which is 4 to the power of k. And that there will be our general or complementary solution. So this is our general solution. So the most important thing is to be able to get the first step correct. You must be able to assume your trial solution of this form, and this solution must be non-trivial, meaning it must not be 0. And after finding an expression for y sub k, you can now find y sub k minus 1, y sub k minus 2, and you plug them into the given difference equation, and you solve for the two values of lambda. And your things will always take, your solution will always take this form if the solutions or the roots are distinct. If the roots are distinct. So here the roots are distinct, meaning they're different. And indeed, we've got negative 1 and 4. So if the roots are not distinct, then multiply any of these terms by the variable k. So meaning you'll have to multiply either this one by k or this one by k. Doesn't matter which one. But in this case, since our roots are distinct, we just leave it like this. So we'll do another example where the roots are the same, and we'll see how we can solve that. And we'll also do more examples similar to the one we did in this lesson. Thank you for watching.